What are applications of expressions? Well, recall it first of all, an expression is notation representing a number. So where did, oh, by the way, quantity is another word that we will often use for number. So where do numbers appear? Well, kind of all over the place, right? So if an expression is notation that represents a number as one way to say it, as up here, we can then also replace the word number here with quantity. So we could say an expression is a notation representing a quantity. Now, by quantity, this sometimes gets people, but we really need to dig into this, right? If quantity and number mean the same, um, we should not just think of a number as being five, which is fine, but also we should think of a quantity or number as being, if as a question whose answer would be a number. So if we can ask a question, often these questions start with a phrase like how many or how much. Those kinds of questions, even if we don't know the number, we ask the question, and the question itself, just asking the question, represents the number or the quantity and therefore is an expression to us. For instance, how many feet off the ground is that airplane? How many people were wrongfully convicted of a crime last year? How much should minimum wage be so that someone can live without debt? These are important questions, right? So, for the safety of airplanes, justice, um, having a living wage, just being able to, pay the bills and all that. These are quantities that are important, and so we write these things down using expressions. Now, one of the key ways that expressions show up, though, is in equations. So let's talk about an application for equations. Recall first that an equation is a statement that two expressions are equal. Equations are actually very useful. In 2 weeks, we're actually going to see this equation, 0.60 times, in parentheses, 32 plus x, close parentheses, equals, and then on the other side of the equation is this expression, 32 times 0.91 plus 0x. Of course, this 0 times x we can get rid of, but that's not the point here. We have this equation. Where did this come from? This equation actually came from the following question. And we're going to look at this question in about 2 weeks. The CDC recommends hand sanitizer that's at least 60% alcohol to deactivate the virus that causes COVID-19, but stores are out of stock due to overpurchasing. You have a 32 fluid ounce bottle of 91% isopropyl alcohol at home. It's a good thing you bought this years ago, but since its strength is more than enough, you don't want to waste it. How much lotion with no alcohol in it should you mix in to create a homemade hand sanitizer that's 60% alcohol? That's very relevant, right? That's a real application of equations. We will use the algebra of equations, namely solving equations, to answer this question that you see here in just 2 weeks' time. More generally, equations capture how expressions are related to each other. For example, the ideal gas law from chemistry, PV equals nRT, is an equation that relates pressure, volume, and so on for a gas. Now let's talk about functions. What are applications of functions? Well, I'd like to, first of all, let's say a function, just as a reminder, is a rule which provides exactly one output for each input. I would like to provide two applications of functions. Just first of all, a function, just from a mathematical standpoint, is a convenient way to model many similar situations all at once. Here's an example. Alex works in a cell phone store with a base pay of $70 for a full workday, plus an $8 commission for each new customer who signs up for a phone plan. If Alex gets 3 customers to sign up in a day, what is their pay? It should be $70, that's the base amount, plus, well, this commission of $8 is paid for 3 times in total, so 8 times 3, which would, of course, be 24, but I don't want to simplify right now. I just want to notice the pattern. I'd rather leave this as 70 plus 8 times $3. If Alex gets 4 customers to sign up in a day, what is their pay? This should now be 70 plus 8 times $4. Now, if we keep doing this for, like, what about if there's 5 customers? What if there's 12 customers that sign up in a day? Alex has a really good day. This will get tedious. So instead, let's just say that Alex earns 70 plus 8x dollars in a day when x customers sign up. So the function f of x equals 70 plus 8x describes Alex's pay if they get x customers to sign up that day. This function models how one quantity, it was sales specifically, translates to another quantity, namely money. The input here has units, number of phone plans, I guess, right? If X is 3, that's 3 phone plans or 3 customers, while the output has units of dollars. Here's a second example. The example situation is the batter opposing the Brewers hits a fly ball, and the height of the ball x seconds after impact is given by negative 16x squared plus 50,168x plus 3 in feet. Now, sorry for the strange numbers, like the 50,000, whatever, but this is actually realistic. I'm using real physics-based data for this. How much time does the catcher have to catch the fly ball? This kind of question can be answered. Now, first of all, at the moment of impact, now x remember was x is the number of seconds after impact. So at the moment of impact, that's when the bat hits the ball is negative 16 times 0 squared plus 50,000 whatever times 0 plus 3 feet off the ground. And 1 second after impact, instead, where the x's are, plug in a 1, and it's that many feet off the ground. 2 seconds after impact, you see. So again, it's tedious to write down all of these, and so this function helps take care of a bunch of situations all at once. The function f of x equals negative 16x squared plus 50,168x plus 3 describes the height in feet, x seconds after impact. This function models how one quantity, in this case it's time, translates to another quantity, in this case height. The input has units of seconds. The time here is given in seconds, while the output has units of feet. The height of the ball is given in feet.